In the days before computers, information was passed around by word of mouth, or for those who were literate, by the written word. For instance, in ancient times it was important that military instructions were kept secret in case they fell into the hands of enemies. Julius Caesar, who lived from 100 BC to 44 BC, used a method of scrambling the letters in a message so that it could only be read by someone who knew the secret of how to unscramble them. Here's a phrase written in classical Latin, and here is the corresponding scrambled phrase. This method of scrambling became known as the Caesar Cipher, and it involved replacing each letter in the message with a corresponding one from the alphabet. Now, I don't speak classical Latin, so let's see it in action using the English language. In fact, the way the Caesar Cipher worked was quite simple. You first decide what your message is, in this case attack at once, then each letter is replaced with the letter 3 steps after it in the alphabet. So the letter A becomes the letter D, T becomes W, and so on. To scramble X and Y, which would go past the last letter in the alphabet, you simply loop around again and start at A. So Y would be scrambled to B, for example. You continue to do this until all letters have been scrambled. So these are the scrambled letters that we're left with. Now, unless you knew how to unscramble them, the message would stay secret. Now let's say that you've received this message from Caesar. How do you unscramble it? Since you know it's been scrambled by moving 3 steps forward in the alphabet, then unscrambling it is simply a matter of moving 3 steps backward. So D becomes A, W becomes T, and so on. In ciphers we call the scrambling process encryption or enciphering, and the unscrambling process decryption or deciphering. What the Caesar cipher illustrates is the way we can take a problem, in this case how to securely send a message, and come up with a solution. The first step was understanding what the essence of the problem was, and then limiting ourselves to the important factors. In this case, the essence of the problem was about hiding the real message from others. Alternative solutions might have been invisible ink, or hiding a message inside another message. In this example, the message is hidden in the first letter of every third word in the sentence. Now, for the Caesar cipher, the idea of shifting the alphabet was okay for the time. Indeed, it's believed that the cipher wasn't broken until many centuries later, so it was definitely a successful solution. The other thing in problem solving is simplification. We do this by removing details which aren't important. In this case, it was decided to limit messages to text and not to numbers or spaces or pictures. Simplifying the problem also simplified the solution, as we don't need to concern ourselves with encrypting text which have spaces and numbers in, or indeed images. Yet another technique in problem solving is dividing a big problem into smaller problems, then solving each smaller problem, and then combining them to solve the original. By splitting the secure message problem into smaller steps of encryption and decryption, the problem became easier to solve. Of course, alternative solutions could be used for the secure message problem. For instance, rather than using an offset of 3, the cipher could have used an increasing offset for each letter, such as 3, 4, 5, and so on. Generally, any problem can be solved in many different ways, but part of the process of problem solving involves deciding which solution is best from those available, but we'll look at this later. Now, you might be wondering what any of this has got to do with algorithms. Well, quite simply, the steps used by the Caesar cipher is an example of an algorithm. That's because an algorithm is just a fancy way of saying the steps to be followed to complete a task. Let's move from ancient Roman times to now and talk about the Caesar cipher in modern day terms, in terms of algorithms and computing. The first thing to say is that whilst a computer program is a way of implementing an algorithm, that doesn't mean that an algorithm is a computer program. It could equally be just a set of written steps for someone to carry out directly. Another term that you'll hear often in computing is abstraction. Abstraction is the process of removing unnecessary detail from a problem until you're left with the right level of detail for that problem. In the case of the cipher, it was to ignore spaces, punctuation and numbers. When we broke the overall problem of hiding messages into a number of parts, we were using a common method for solving problems which is given the name decomposition. Decomposition just means breaking a problem into smaller subproblems. We keep on doing this until each part is easy to solve. Abstraction and decomposition are ideas used all the time both in algorithms and in computing generally. Whilst algorithms can be written down in plain English, it's more usual, at least when you're a beginner, to document them either as a flowchart or as pseudocode. We'll cover pseudocode in a later video. A flowchart is a diagram that represents a process. In our case, we'll use them to represent the steps of the algorithm. The different symbols represent different kinds of step, and the connecting arrows show the flow and sequence. Let's take a look at creating a flowchart for the Caesar Cipher. This is going to be a flowchart for how the cipher would work in Roman times and not using a computer. If you recall, the basic steps of the cipher were write down the plain text message, encrypt it, send the message, decrypt it, and read the message. The first step is to show the start of the process. That's shown with a terminator symbol. Next, we use a process symbol to show a task. Here the task is write plain text. This produces some data, or input-output, of plain text shown by the data symbol. We show which steps follows which by the connectors. Encrypting the message is the next step, but rather than using a process symbol, we use a defined process symbol, meaning that the steps inside are defined elsewhere in another chart. In programming, the defined process symbol turns into a subroutine. The encrypt step produces encrypted text as the output. We continue in the same way for the remaining steps, and choose the appropriate symbols for sending the message, decrypting, and reading the message. Finally, we end with a terminator end. Let's look inside the encrypt defined process and see if we can understand what's going on. To help, we'll use a trace table, which is a place where we record bits of relevant data as we run through the algorithm. As before, we show the start and end of the process and, as an input, the plain text. In the trace table, we'll keep it simple and just record the plain text and the encrypted text as we go. Now the steps are to read the next letter from the text, find that letter on an alphabet wheel, choose the third letter along and write that down as the encrypted text. The next symbol is a decision. In it we ask the question whether the plain text letter is the last one. If it is, we end this process. If it's not, then we go back, read the next letter and continue. Running through the steps, we start with an A, find it on the wheel, choose the third letter along, D, and write this down. We've more letters to do, so let's repeat until it's all done. All done. You can see that the trace table helps us to visualize how the algorithm works in practice and to discover any bugs in our thinking. Well, that's our first look at algorithms. We've learned that algorithms have been around an awful long time and aren't just about computers. We've also seen how to create them, how to document them with flowcharts, and how to understand how they work with trace tables. Of course, there's a lot more to them than we've covered here, so we'll be coming back to them again for sure. But in the meantime, why not try picking a problem and creating some algorithms of your own?